Welcome to aminacademy.com. In discrete mathematics, let us discuss about mathematical induction, some introduction. Suppose you have an infinite ladder, that means very big ladder, and we want to know whether we can reach every step on this ladder. You should know two things. First one, you can reach the first rung of the ladder. Second one, if we can reach a particular rung of the ladder, then we can reach the next rung. Can you conclude that we can reach every rung? We know that we can reach the first rung and the ladder, moreover, because we can reach the first rung. Then we can also reach the second rung. It is the next rung after the first rung. Like this continuing, we can reach the second rung, we can also reach the third rung. Continuing in this way, we can show that we can reach the fourth rung like continuing. It is called mathematical induction. That means what? One by one steps increasing. Mathematical induction is an extremely important proof technique that can be used to prove assertion of this type. As we will see in this section, in this videos and in subsequent videos, we will discuss about mathematical induction by using some example problems. Here, in mathematical induction, is a method of proving that statement is true for every natural numbers. That is, that the infinitely many cases. All hold informal metaphors help explain this technique, such as falling dominoes or climbing in the ladder. Mathematical induction proves that we can climb as high as well, like on a ladder, by proving that we can climb onto the bottom rung, the basic steps, and that from each rung we can climb up to the next one, that is next step. A proof by induction consists of two cases. The first, the base case, proves that a statement for without assuming any knowledge of other cases. The second case, the induction step, proves that if the statement holds for any given cases, then it must also hold for the next cases. These two steps establishes that the statement holds for every natural number. The base case does not necessarily begin with, but often with, and possibly with any fixed natural numbers. Establishing the truth of the statement of all natural numbers, then we can completely prove the statement. Take some example to prove. We know that sum of natural number, that is 1 plus 2 plus 3 up to n, is n into n plus 1 by 2. By mathematical induction, let us try to prove this. Look at here, that the statement, let P of n. P of n is our statement, which is equal n into n plus 1 by 2. First, we introduce P of 1, the base step, P of 1. P of 1 means that here this first left hand side first term is 1, which is equal here n into n plus 1 by 2, that is 1 into n is 1 plus 1 by 2, which is equal 2 by 2 equal 1. That is, we have 1 equal to 1, that is true for P of 1. Now some other number like P of k, integer k, positive integer k for this, P of k equal, that is 1 plus 2 plus 3 up to k values, equal that right hand result is n into n plus 1 by 2, that is n is k, n plus 1 is k plus 1 by 2. Under this assumption, we must be shown that p of k plus 1 also true. Look at here. Here p of k plus 1 is equal 1 plus 2 plus 3 going continuation up to k plus 1, which is equal n into n plus 1 by 2. N is k plus 1 and n plus 1 is k plus 1 plus 1 by 2, which is equal k plus 1 k plus 2 by 2. That is equal look at here. Further you can explain this k plus, that is k into k plus 1 plus 2 into k plus 1. We are expanding these two things. Here k into k plus 1 and 2 into k plus 1 by 2. Therefore, this is last equation shows that p of k plus 1 is true. Therefore, you can say p of k plus 1 is true. Then from this about discussion, we can say p of n, which is equal 1 plus 2 plus 3 up to n integer, which is equal n into n plus 1 by 2 for all positive integers n. For all positive integers n. That means first here we discussed about what is mathematical induction. It's useful for proving mathematical statements and how we are proving by using some example problem. Look at here. This is a mathematical induction. We have to prove that sum of natural numbers up to n terms is equal to n into n plus 1 by 2. For the base step, we have to prove for n equal to 1. N equal to 1 means the first n equal to 1 is first n equal to p of 1 equal to 1 is 1, because we are substituting n equal to 1. 1 plus 1 by 2, so 1 into 2 is 2, 2 by 2 is 1. So a basic step, p of 1 is 1 both side here. Some other integer k values other than 1, that is p of k equal to 1 plus 2 plus 3 up to k values, which gives instead of n we are substituting k, that is k into k plus 1 by 2. Now further it is true. That is true. Therefore, we are continuing to prove with the next integer of k, that is k plus 1. We are using p of k plus 1 is 1 plus 2 plus 3 up to, then continuing up to k plus, next step is k plus 1. So instead of k we are writing k plus 1, that is n is k plus 1, n plus 1 is k plus 1 plus 1 by 2. By simplifying, k plus 1 plus k plus 2 into k plus 2, then splitting, that is k plus, distributing k plus 2, that is k into k plus 1 plus 2 into k plus 1 by 2. Which is that is here we can write which is equal further k plus 1 into k plus 2 by 2. Therefore, you can say p of k plus 1 is 2. Similarly, p of n we can write p of n equal to 1 plus 2 plus 3 up to n equal to n into n plus 1 by 2. That is, it's for all value the positive integer n, it is 2. Therefore, we proved this mathematical statement by mathematical induction. If you have done, please subscribe our YouTube channel.